Acid-base equilibrium. Solubility and the common ion effect influence on acid-base reactions. In this tutorial, we will be looking at factors that affect solubility, the effect of common ions on solubility equilibria, and a worked example. Factors that affect solubility. Two factors that affect the solubility of ionic compounds are the presence of common ions and the pH of the solution. The solubility of a slightly soluble salt is decreased by the presence of a second solute that contains a common ion. Changes in pH and the resulting effect on the solubility of a salt can be conceptualized with an understanding of the common ion effect. The dissolution of a salt is a reversible process that can be influenced by environmental factors such as pH or other dissolved ions. The solubility of a salt is pH sensitive when one of the constituent ions is a weak acid or base. These effects can be understood qualitatively using Le Chatelier's principle. Let's look at an example. The value for KSP for manganese 2 hydroxide, MnOH2, is 1.6 times 10 to the negative 13. Calculate the molar solubility of MnOH2 in a solution that contains 0.02 molar NaOH. So our strong electrolyte in this situation is NaOH solid dissociating into Na plus 1 ions and OH minus 1 ions. The equation for the dissolution of the salt is MnOH2 solid in a reversible reaction producing 1 mole of Mn plus 2 ions for every 2 moles of hydroxide ions. The presence of either Mn plus 2 or OH minus 1 in a solution reduces the solubility of MnOH2, shifting the solubility equilibrium to favor the formation of reactants. The KSP accepted value for MnOH2, a slightly soluble compound, again, is 1.6 times 10 to the negative 13, a very small number. The value of KSP is unchanged by the presence of additional solutes. Due to the common ion effect, the solubility of the manganese 2 hydroxide salt decreases in the presence of common ions. So the common ion between these two equations is the OH minus 1. Because this common ion exists between these two equations, equilibrium is going to shift to favor the formation of reactants, decreasing the amount of Mn plus 2 ions and OH minus 1 ions in solution. Let's look at this quantitatively. The KSP expression is used to determine the concentration of the ion that comes only from the MnOH2. A Rice table can be used to present initial and final equilibrium concentrations. In the beginning, we're going to recognize that the MnOH2 is not going to be included because MnOH2 is a solid. Initially, we're going to have no Mn plus 2 ions in solution, and the amount of hydroxide ions in solution is due to the presence of the hydroxide ions from the sodium hydroxide, which has a value of 0.02 molar. Our change is going to be represented as a plus X, which is the amount of Mn plus 2 ions that will be in solution, and 2X, which represents the amount of hydroxide ions from the MnOH2. So we're going to write our KSP expression for MnOH2. Then we're going to substitute in our X values for the concentration of Mn plus 2 and OH minus 1. We're going to cross out the 2X value that is associated with the hydroxide ion because the term X is assumed to be negligible compared to the 0.02 molar value from the NaOH. I'm going to plug in my values for KSP, and I'm going to square the 0.02 value. Finally, I'm going to solve for X. So X is equal to the concentration of Mn plus 2, which is 4 times 10 to the negative 10 molar. Finally, I'm going to take this value and put it into my rice table. So the Mn plus 2 value is 4 times 10 to the negative 10 molar, and my value for the hydroxide is still going to be 0.02 molar. Even without the common ion effect, the solubility of MnOH2 is very small, as stated before, as it is 1.6 times 10 to the negative 13. Thus, the 0.020 molar concentration of hydroxide from the NaOH can be assumed to be much greater than the small additional concentration resulting from the solubility of MnOH2. That is, X is much smaller than 0.020 molar, and 0.020 plus 2x is approximately equal to 0.020 molar. Now we're going to calculate the value of X if the hydroxide common ion from the NaOH was not present in the MnOH2 equilibrium system. So we're going to start out by writing our KSP expression. Next, we're going to plug in the X values. X times 2x squared is going to give us KSP is equal to 4x cubed. We're going to plug in our KSP value that is given to us. Finally, we're going to solve for X. X is equal to the concentration of Mn plus 2, which is 3.4 times 10 to the negative 5 molar. So the concentration of the Mn plus 2 ions calculated at 3.4 times 10 to the negative 5 molar without factoring in the common hydroxide ion is notably higher compared to the concentration of Mn plus 2 ions influenced by the presence of the common hydroxide ion from NaOH. So what did you learn? We talked about factors that affect solubility, the effect of common ions on solubility equilibria, and then we did a worked example at the end. Need more help? Feel free to contact me. Have a great day.